In my earlier classes, I have already mentioned you about some of the macromolecules present in the cell. Those macromolecules are either protein or carbohydrate or nucleic acid. And most of these macromolecules were soluble in nature. Today, I will be talking about a new molecules which are there in the cell, but it has got little different behavioral or different properties, and those type of macromolecules are called lipid. Now, if we see the lipids, then lipids are the non-polar molecule that includes fat, cholesterol, fatty acid, lipid soluble vitamins, waxes, soaps, and so on. Lipid consists of a broad group of compounds that are generally soluble in organic solvents and only sparingly soluble in water. Now, when we are talking about this lipid molecule is present in every cell, irrespective of microbial, plants and animals. So, if we want to extract this lipid molecule, being non-polar in nature, we have to use some solvent like chloroform, benzene and so on to extract this lipid molecule from the cell. Now, obviously, when I am talking about this particular macromolecule, so if we classify these entire lipid molecules, then we will find that the entire lipid molecule can be divided into two broad heads like saponifiable lipid and non-saponifiable lipid. That means one type of lipid has some characteristics of soap formation, and these type of lipids are further divided into simple lipid and complex lipid. So, these particular classifications has been done based on the structural or the structural behavior of this lipid content of the lipid molecule. Now, another group is the non-saponifiable lipid. Steroid and prostaglandins are some of the example of that. Now, as I have mentioned that the classification is done based on the backbone structure of these lipid moieties. So, obviously, the structure of these lipid molecules are coming to the picture. Now, when we are doing this classification, fatty acid is one of such long chain linear unbranched hydrocarbon which is present in the lipid moieties. It has got a carboxylic acid group present attached to its core moieties. Triglyceride, phospholipid, glycolipid, icosanoids lipid, steroids, lipoproteins are the different types of lipids which are there present in the lipid family. Now, let us come one by one. When we are talking about this fatty acid, it is the long chain linear hydrocarbon having the carboxylic acid end. Now, that means it has got a carboxylic acid end. Now, if we are talking about this particular acid, then this carboxylic group which is there, and if we consider about this chain, then we can find that this fatty acid has got one carboxylic end group which is polar in nature and non-polar chain like structure, that is the tail part. One is the head, another is the tail, and this hydrocarbon chain is the long chain which is attached to this carboxyl end of this fatty acid. The chain length can be varied from 4 to 30. the carbon are numbered starting from this carboxylic end. That means this is the carbon atom number 1. Then it is 2, 3, 4, 5, 6, 7, 8, 9, and that way the numbering is done. Now, it is amphipathic in nature. That means it has got one polar end and one non-polar end. Fatty acids are maybe saturated or unsaturated. That means when we can tell that fatty acid is saturated, that means entire fatty acid can be divided into two parts. One is called the saturated fatty acid, another is the unsaturated fatty acid. Now, when this is saturated fatty acid, when there is no double bond present in this fatty acid, only the linear chain along with a carboxyl end, and this chain length may get very different depending upon the nature of that fatty acid. But when the double bond is present in between the non-polar tail group, then we call that type of fatty acid as the unsaturated fatty acid. All naturally occurring double bonds have a cis configuration. So, most of these double bonds are either, it can be found either in the cis form or in the trans form. So, in most of the cases, these fatty acids are found in the cis form. I will be coming to this, the positional, what is cis and trans gradually. Now, two or more double bonds exist as non-conjugated double bonds, and longer fatty acid and saturation increases the melting point of the fatty acid. Fatty acid gets ionized at physiological pH, that means at pH around 7.4. Now, as I have already discussed the structure, you see here is a long chain which is the tail group, non-polar hydrophobic tail, which is water insoluble, and here the polar end which is hydrophilic in nature, and this is the head group. So, we represent this COOH as the polar and the tail which is attached as the non-polar. This fatty acid is once again classified into saturated, unsaturated. Sometimes it is the branched fatty acid, substituted fatty acid, and cyclic fatty acid. That means besides this saturated and unsaturated, we can also get this fatty acid in a much more complex form. That means sometimes we are getting it in the branched condition, substituted condition, sometimes we are getting in a cyclic form. When we are talking about the unsaturated fatty acid, it may be monoenoic acid, dienoic acid, trienoic acid, tetraenoic acid, and so on. Now, coming to the saturated fatty acid. As I have mentioned already that saturated fatty acid has no double bond within it, and if we are considering the total number of carbon present is 14, then myristic acid is one of the example. Now, here you see total C carbon, the number of carbon atom present in this fatty acid is 14. We can get this type of fatty acid in butter fat, coconut oil, and so on. When we are considering the 16 carbon molecule, then it is the palmitic acid. Here also no double bonds are there. So, here 18 carbon is the stearic acid, and so on. This way the number is getting increased and the properties and the characteristics are also getting changed. Now, this palmitic acid is found in lard, beef fat, and so on, coconut seed oils and so on. So these are the common example of saturated fatty acid. Now coming to the nomenclature. Now the systematic name of the fatty acid is derived from the name of the parent hydrocarbon by the substitution of OIC, oic. For example, the C18 saturated fatty acid is called C18, that means 18 carbon containing chain, that is octadecanoic acid. So because the parent hydrocarbon is the octadecan, C18 fatty acid, if it is having a double bond, then it is called octadecanoic acid. If two double bonds are there, then octadecadienoic acid. And with three double bonds, then octadecatrienoic acid. Depending upon, as I have mentioned, that monoenoic, dienoic, trienoic, tetraenoic, in that way the naming has been done. Now sometimes we are getting some symbol like 18:0. Sometimes we are getting 18:1. Sometimes it is 18:2. What does it mean? It means that fatty acid is having 18 carbon atom and it has no double bond. That means it is a saturated fatty acid. When we are getting 18:1, that indicate that 18 carbon atom containing fatty acid, that chain, and one double bond is present in this. 18:2, that means 18 carbon fatty acid, two numbers of double bonds are present in this particular molecule. So how it will be? And this is the meaning of this particular 18:1, 18:2, 18:0 and so on. The position of double bond is represented by the symbol delta followed by a superscript number. That means if suppose the bond is cis type of bond and if it is written delta to the power 9, what does it mean? That means that this fatty acid is arranged in a cis configuration and this double bond is present in carbon atom 9 and 10. So, and if it is suppose trans delta 2, it means that there is a trans double bond between carbon atom 2 and 3, and in this way the numbering is done. Now, if suppose we are talking about the cis and trans configuration, then we can find that a cis configuration means that the adjacent hydrocarbon atom are on the same side. See here, it is on the same side of the double bond. The rigidity of the double bond freezes the conformation, and in the case of cis isomer causes a chain to bend and restrict the conformational freedom of the fatty acid. That means in this type of configuration we can find a kink in this fatty acid chain where this double bond is present. In case of this trans fatty acid, the next two hydrogen atoms are bonded in the opposite side of the double bond. As a result, they do not cause the chain to bend much and their shape is similar to straight saturated fatty acid. So, this is the trans form of this fatty acid, trans form arrangement. And here, as their positions are like this, they don't we don't get much kink or bend in this double bond side. Now, if we see some of this example of the mono unsaturated fatty acid, polyunsaturated fatty acid, then we can find that palmitic acid, oleic acid, linoleic acid, linolenic acid, and so on. So, this depending upon the carbon chain and number of fatty acids, the naming has been done. So, here in case of palmitoleic acid, here you see here only one double bond is there. When we are considering oleic acid, then here we can find that here also single double bond is there. In case of polyunsaturated fatty acid, linoleic acid, we are getting two double bond. Linolenic acid, we are getting three double bond, and so on. So, this way the chain is getting increased. So, here you see this is the saturated fatty acid, this is the unsaturated fatty acid. See 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10 carbon atom. So, when I am talking about cis delta 9, that means in between 9th and 10th carbon atom the double bond is present and it is the oleic acid. Now, coming to this saturated fatty acid, as I have already mentioned that it does not have any double bond, closely packed, strong attraction between chain, high melting point, solids at room temperature, and it is the well established fact, and World Health Organization also claims that if a person is continuously taking a saturated fat or a saturated fatty acid, then he or she will have definitely the cardiac diseases with the continuous taking of the this saturated fats. So, what is the unsaturated fatty acid? It contains one or more double bond. If one double bond is there, it is mono. If it is more than 1, 2, 3, that is the polyunsaturated fatty acid, that is PUFA. Non-linear chains do not allow molecules to pack closely. Few interactions are there between the chains, and that is the reason it has got a low melting point, liquid at room temperature, and unsaturated fatty acid can occur in a cis or the trans configuration. Now, if we see the structure of stearic acid, see here the carboxylate and straight chain fatty acid. Whereas, in oleic acid, you see here also it is 18 carbon molecule, and here the double bond is present, it is also ending with the carboxylate. So, it starts with the carboxylate, and when it is coming 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10, this double bond is there. Say there is a kink, there is a bend to this, and that is making the inter characteristics of the molecule different. Now, how if the stearic acid has got melting point of 71 degrees centigrade, because it is a packedly, it is closely packed molecule, and see here melting point is 71 degrees centigrade. In case of oleic acid, it is 13 degrees centigrade, and in case of linoleic acid, you see here two double bonds are there, and you see the melting point is minus 5 degrees centigrade. So, with the number of double bonds, the characteristics and the behavior of the entire molecule is getting changed. If we come to this hydrogenated fat, hydrogenation leads to either saturated fat or trans fatty acid. The purpose of hydrogenation is to make the oil and fat more stable to oxygen and temperature variation, and it also increases the shelf life of the product. Now, one of the example of this is the Crisco or margarine, etc. Unsaturated fatty acid may be converted to saturated fatty acid by simple hydrogenation reaction. By the addition of hydrogen, we know that alkene can be converted to alkane, and if we see the hydrogenation reaction, so this type of reactions are taking place resulting in the hydrogenated fat, and dalda is one of the example of this hydrogenated product. Now, this is, as I have already mentioned, about this classification based on the backbone structure of the fatty acid. This fatty acid, this lipid molecule can also be classified based on its biological structure and function. It can be divided into two parts. One is the storage lipid, another is the structural lipid. Now, when we are coming to the storage lipid, the fats and oils used in stored form of energy in living organisms are derivatives of the fatty acid. The fatty acid are hydrocarbon derivatives. Two types of fatty acid containing compounds are there. Triglycerol and waxes are the example of the storage fatty acid. Storage lipid molecule. Now, when we are talking about the properties of the fats and oils, fats are solid or semi-solid in nature, oils are liquid, melting point and boiling point are not usually sharp in case of these fats and oils. When shaken, it forms the emulsified product, and pure fat and oils are colorless and odorless, and once we are getting some odor or color, we can easily detect that this particular product is contaminated. Now, coming to the wax. Wax is the example of simple lipid. Now, it is the simple ester of fatty acid, and it has got a very long chain of monohydric alcohol which is attached to its structure. Now, when it is warm, we are getting a soft form of wax, but when it is at room temperature, then we are getting a solid mass of wax. Now, when we see the different forms of this, the wax is present in different biological molecules, then we can find that it is acting as a coating material of many biological molecules. Say for example, it is present in the skin, fur, feather, etc. It is in some animal, wax is also present on the exoskeleton. In case of some insect, it is present on the exoskeleton, and this particular molecule has got fatty acid, long chain fatty acid and long chain alcohol within its core moieties. It is also present in higher plants and animals too. Now, some of this example, this bee wax is one of the example of the wax. Now, it is also this bee wax also contain the fatty acid and some free alcohol within it. Now, coming to the structural lipid, if we see the structural lipid, that indicates, the name itself is telling that it is giving the structural support or strength to the membrane or the cell wall of the cell. If we see the membrane lipid is one of the very important example of this, where these lipids are playing a very important and significant role. It can be divided into different parts. say for example phospholipid, glycolipid and archibacterial ether lipid. So, these are the different composition of this structural lipids which are mainly present in the cell wall or cell membrane of the cell of any animal or plant cell. Now, glycerophospholipid, sphingolipids are the example, or galactolipids are the example of such type of lipid molecule, where this either glycerol or sphingosine are present as the core moieties. Now, I will be coming in details about the structure gradually. Now, if we see the sources of different lipid molecule in animal as well as plant, we can find that in animal system whatever is the lipid molecule present are mostly the saturated form of lipid molecule. Here the proportion of saturated versus unsaturated, you see, starting from butter, beef, chicken and animal fat, lard, eggs, etc. You see here the proportion of unsaturated fatty acid is much smaller compared to the plant sources. Here the amount of unsaturated lipids are, or unsaturated fatty acids are more compared to the animal fat, and here is the difference between plant lipid and the animal lipid. Coming to the triglycerides. Triglycerides are formed from a single molecule of glycerol. Now, if we see the structure of glycerol, then what we can see? Glycerol is a 3-carbon molecule, CH2OH, CHOH and CH2OH. This is the glycerol moieties. So, here in triglycerides, a single molecule glycerol is there combined with the 3 molecules of fatty acid. The glycerol molecules has 3 hydroxyl OH group. This 3 hydroxyl OH group within it. Each fatty acid has a carboxyl end, that I have already mentioned, that any fatty acid has got a carboxyl or the polar end within it. So, in triglycerides, the hydroxyl group of glycerol joins the carboxyl group of the fatty acid to form the ester bond. That means, this hydroxyl group and carboxylic group is getting linked with each other with the ester linkages, and they form the triglycerides. Now, if we see the properties of the triglycerol, then we can find that the melting point of triglycerol is determined by its fatty acid component. Melting point increases with the saturated fatty acid and its chain length. All the triglycerides are insoluble in water and do not tend themselves to form highly dispersed micelles. But mono and diacyl glycerol have appreciable polarity because of their free hydroxyl group, and thus they can form the micellar structure. Mono and diacyl glycerol find wide use in the food industry. Acyl glycerol is soluble in ether, chloroform, benzene and also in hot ethanol. Now, when I was talking to you about the saponifiable lipid, now soap is one of the example of saponification process. Now, here if we see the types of soap, we can classify that sodium soap, which is an ordinary hard soap, potassium soap, it is the soft soap which is used for the shaving purposes, castile soap, that is the sodium soap with olive oil, green soap, it is the mixture of sodium and potassium linseed oil, transparent soap, it contains sucrose along with its structure, floating soap, it contains air. Calcium and magnesium soaps are very poorly water soluble in nature, and these are the different types of soap molecules. When we are coming to this phospholipid, we can find that the major component, it is one of the major constituent of the cell membrane. Phosphoglycerides contain a phosphate group. Nitrogenous or non-nitrogenous group is also present in it, and it is the structural component of any cell. Phospholipids are generally composed of fatty acid, nitrogenous base and phosphoric acid, and either glycerol, inositol or sphingosine within it. See, I have already talked to you about this glycerol molecule, CH2OH, CHOH and CH2OH. See, here in this core moieties, see, first group is attached with the fatty acid, second group is also attached with the fatty acid, and third group, you see, one phosphate is attached and one X is there, and this X may be the precursors for the phospholipid, and it may be phosphatidic acid, it may be phosphatidylcholine, it may be phosphatidylserine, phosphatidylethanol-amine and so on. So, this is the core structure, this is the glycerol structure along with these fatty acid hydrophobic tails which are there, and to this phosphate moieties are attached, and to this X group where these precursors of the phospholipid, phosphatidylcholine, phosphatidylserine, phosphatidylethanol-amine, any moieties can come and join and form the molecule. Some phospholipid which has the ether linked fatty acids are there in the living system, that some of the examples are vertebrate heart tissue uniquely enriched with this type of ether lipids, plasmogens, that is half of these heart tissues are the plasmalogens, and platelet activating factors are also the example of the ether linked fatty acids. Coming to the sphingolipid. Sphingolipids are derivatives of the lipid sphingosine and are important membrane component in both plant and animal cells, especially large amount of brain and nerve cells. So, these particular lipid moieties are mainly present in the brain and nerve cell and playing a very significant role. It has a long hydrocarbon tail and polar domain that includes an amino group. Sphingosine is present as a core moiety instead of glycerol. Now, in case of this phosphoglycerol, what I have told here, if you see this main, it is the glycerophospholipid, here the main moieties are the glycerol moieties. But in this case, in case of sphingolipid, if we see the structure, here we can find this is the sphingosine molecule, along with this one fatty acid is attached, and this X group may be phosphocholine, glucose, oligosaccharides, which can be di, tri or tetrasaccharides. Thus, the oligosaccharides can be a simple sugar to a complex sugar molecules which are attached to the sphingosine group. Lactosyl ceramide and gangliosides are the examples of oligosaccharide containing sphingolipid. The other examples of sphingolipids are sphingomyelin, neutral glycolipid, etc. Sphingosine. That means sphingolipid, if we see, then sphingosine has got a lipid sphingosine moiety is within this, and which is replacing the glycerol of the other type of fatty acid. All sphingolipid contain the three characteristics building block component: one molecule of fatty acid, one molecule of sphingosine, and or one of the derivatives of the polar head group, which is very large and complex in some sphingolipid. So these are some of the example of the sphingolipid. Now coming to this sphingomyelin, it is a ceramide. The amino group of sphingosine can form an amide bond with the fatty acid carboxyl group to yield a ceramide. So here, this is the bonding, which is this ceramide. This is the amino group which is getting bonded. It is ubiquitous component in the animal cell membrane, where it is by far the most abundant sphingolipid. It can comprise much 50% of the lipid contains the tissue, though it is usually found in lower concentration than the concentration of phosphatidylcholine which is present in the cell. Similar to that is another type of lipid which is called as glycolipid, as the name itself indicating that in glycolipid they contain the carbohydrate moieties within it. That means the sugar moieties are there, which has got linked with the beta linkages. As I have already told you, alpha linkages, beta linkages. So here it is attached with the beta linkages, and polar head group is there for the sugar. Their role is to provide energy and also act as a marker for cellular recognition. So this is the major activities of the different types of lipid molecule. Now I will be coming to the another type of lipid moieties, which is called the steroid. Now the steroid is a type of organic compound that contain a specific arrangement of 4 rings that is joined with each other. That means if we see the structure of steroid, we can find that, you see, it has been denoted as A ring, B ring, C ring and D ring. Now if we see A, B and C, then we can find that this A, B and C ring are cyclohexane ring. Along with this cyclohexane, the D ring which is attached is the cyclopentane ring. Now this ring is also called as parhydrocyclopentanophenothrin ring. Now this styrene core of steroid is composed of 17 carbon atoms bonded together to form a 4-fused ring. 3 are cyclohexane, 1 is cyclopentane. So that means this is a very complex water insoluble lipid moieties. Cholesterol is one of such example of this steroid. Cholesterol has a molecular formula of C27H45OH. That means it has got one hydroxyl group which is polar in nature, which makes it soluble in water. Thus, and this mol2 atom hydroxyl group structure makes the cholesterol and alcohol too. It is the major sterol in the animal tissue. It is amphiphilic in nature, amphipathic in nature. That means on the 3rd carbon of this first A ring, that hydroxyl group is attached. The polar head, the hydroxyl group at carbon atom number 3, and a non-polar hydrocarbon body as long as 16 carbon fatty acid in its extended form. So, total it has got 27 carbon atom and 16 carbon fatty acid is also attached as a alkyl side chain molecule, and this is the steroid nucleus, and here one hydroxyl group is attached on the carbon atom number 3. While coming to phytosterol, phytosterol is also called the plant sterol, are a group of steroid alcohol naturally occurring in plant. Phytosterol occurs naturally in small quantities in vegetable oil, especially in corn oil, soybean oil, etc. They act as a structural component in the cell membrane, and it also acts as a food ingredient or additives, that is phytosterol have cholesterol lowering properties. That means this phytosterol, as I have already mentioned, that cholesterol is present in the animal system. Similarly, phytosterol is found in the plant system. When we are coming to this ergosterol, it is also a sterol. It is a biological precursor or the provitamin of vitamin D2. It is turned into biosterol by ultraviolet light and is then converted into ergocalciferol, which is a form of vitamin D. Ergosterol is a component of fungal cell membrane serving the same function that cholesterol serves in the animal cell. Ergosterol is also used as an indicator of the fungal biomass estimation. Now, this ergosterol, as I have told, that phytosterol is present in the plant, ergosterol is also present in another type of microbial world, that is the fungus, the filamentous fungus. In any case of this fungal biomass, this ergosterol is present. Coming to the another component, that is the terpenes. Terpenes are the large and varied class of hydrocarbon produced primarily by the wide variety of plant, particularly conifers and some insect such as termites or swallowtail of butterflies. Now, this is the isoprene molecule, and when two such isoprene molecules are coming in association with each other, they form the terpenes. It is a simple lipid but lack fatty acid component within its core moieties. It forms the combination of two such moieties. That means one isoprene molecule is having 5 carbon. Now, when two such moieties are associated with each other, so total carbon of carbon atoms present in that structure is C10. So, monoterpene is the example of that. It is made up of 2 isoprene unit. When 3 such isoprene molecules are associated, it is called sesquiterpene. When 4 isoprene units are there, it is called diterpene, terpenes, and so on. If we see the other terpenes, then tetraterpenes are also present, where the total number of carbon atom is 40, are not as common as mono, di and triterpenes. It includes the carotenoid such as beta carotenoid as a precursor of vitamin A, or lycopene of the tomatoes. Lycopene is the color component. Usually colorful compound due to highly conjugated systems are there. Polyisoprenoids or polyprenols consist of numerous isoprene adducts, that is 8 to 22 of such, and side chain of vitamin K, vitamin E and coenzyme Q are some of the example of polyisoprenoids molecule. If we say the function of terpenes, then terpenes and terpenoids are the primary constituents of the essential oil of many types of plants and flowers. One of the main application of these terpenoids are in the field of medicine, such as aromatherapy. The synthetic variation and derivatives of natural terpenes and terpenoids also greatly expand the variety of aromas used in the perfumery and flavors, which is used in the food industries or food additives. Vitamin A is an example of a terpene molecule. Now, if we are talking about this particular terpene, that is geraniol, limonene, menthol and so on, these are some of the examples of this flavor component or constituents, which are nothing but the terpene moieties. Now, when we are coming to these micelles, the micelle is the aggregate of surfactant molecule dispersed in liquid colloids. Now, as I have already mentioned you that while discussing the structure, we have seen that fatty acid has got a polar end and a non-polar tail. Now, when a typical micelle in aqueous solution forms an aggregate with the hydrophilic head region in contact with the surrounding solvent, sequestering the hydrophobic tail region in the micelle's center. Now, see, when it is in the aqueous environment, what is happening? These heads, all the heads in the aqueous environment, what is happening? This aqueous, if it is the aqueous environment, then aqueous environment is very good for this hydrophilic molecule to go, and it is not at all suitable for the hydrophobic. So, this is the aqueous. So, hydrophilic and polar head is getting exposed outside, and it is just bringing the hydrophobic tail to inside, and when such type of associations are there, then it forms the micelle structure, and this is the micelle in the aqueous solution. And when it is present in the bilayer formation, here is the polar head, here is the polar head and non-polar tails are there, and when the two bilayer forms are there, see here the polar head and non-polar tails. Here also you see the outer layer, the polar head and non-polar tails are there, and when it forms this type of moieties, it is called the liposome. Now, the function of these micelles, the micelle formation is essential for the absorption of fat-soluble vitamins and complicated lipid within the human body. Bile salts formed in the liver and secreted by the gallbladder allow micelles of fatty acid to form. This allows the absorption of complicated lipid, that is the lecithin type of lipid, and lipid soluble vitamins, that is vitamin A, D, E and K within the micelles by the small intestine. When surfactants are present above the critical micellar concentration, they can act as an emulsifiers that will allow a compound that is normally insoluble in nature. Coming to this liposome, the liposome, as I have mentioned, that the liposome is a tiny bubble vesicles made up of the same material as a cell membrane is. It is a form of micelle liposomes are filled with the drugs and used to deliver drugs for cancer and other diseases. So here this aqueous head this is the polar head, and this here also the polar head, and it is the bilayer, and it hydrophobic inside, and it helps the drug to transport from one place to another, and this type of system is used for drug delivery. Liposome can be used as a carrier for delivery of dyes, textiles, pesticide for plants, enzymes and nutritional supplement to foods, and cosmetics to the skin. Coming to this lipid in the cell membrane, the cell membrane consists of primarily the thin layer of amphipathic phospholipid molecules, and here you just see this lipid bilayer are there, this polar head, and here also lipid, this polar heads are there and non-polar tails are there inside. It is a spontaneously arranged so that the hydrophobic tail region is shielded from the surrounding polar fluid, causing the more hydrophilic head region to associate with the cytosolic and extracellular phases of the resulting bilayer. This forms a continuous spherical lipid bilayer. Now, if we come to this lipoprotein, we can find that a lipoprotein is a biochemical assembly that contains the polar protein. It contains both proteins and lipids whose function is to transport water insoluble lipid in the water-based bloodstream. That means this lipoprotein is mainly acting in the transport of water insoluble lipids from one side to another through the bloodstream. These lipids or their derivatives may be covalently or non-covalently bound with the protein molecule. Many enzymes, transporters, structural proteins, antigen, adhesin and toxins are some of the examples of lipoprotein. Now, if we see the function of lipoprotein, then the main function of lipoprotein particles is to transport water insoluble lipids, that is fat, and cholesterol around the body in the blood, that means through the bloodstream. The lipids are often an essential part of the complex, even if they seems to have no catalytic activity by themselves to isolate transmembrane lipoprotein from their associated membrane, that is the reason detergents are often used for this purpose. Now, if we see the main function of lipids, then we can find that the main function is the structuring the cell membrane, energy storage, transmission of informations in the cell, that is the signal transduction, and cellular metabolism, that is the fat soluble vitamins, that is vitamin A, D, E and K are required for metabolism, which are usually acting as an coenzyme. That means we can find that lipid is one of such macromolecules which are present and they do not have any catalytic activities, but it is present within the cell system in a conjugated form, and it is forming the complex structure with other different macromolecules which is present within the cell system, and it performs different activities. The major role is the soluble, the polar and non-polar end which are there is because of this amphipathic in nature, the polar head and non-polar tails are getting associated, and they are just doing the function of by exposing the head to the aqueous phase and tail away from that particular environment, and they do different function, drug delivery and different lipid the water insoluble transportation of different biomolecules from one side to another. So with this, today I am concluding this, the macromolecule, which is entirely different, its character is entirely different from the other macromolecules which we have already discussed and we have learned. Thank you very much.